afternoon, everybody. Hope you're all healthy and safe. Let us continue with our lecture on self-adjoint operators. So in this lecture we shall be discussing about corollary of the first Hilbert-Schmidt operator. So the corollary is as follows. Let T from H to H be a self-adjoint compact operator, and let lambda n plus 1 plus greater than 0. So that is for any value of n there is at least n plus 1 positive eigenvalues. Okay, so the operator T has many eigenvalues. They can be positive and negative. That's what we had discussed. We gave the notation for negative eigenvalues to be lambda I minus and the positive eigenvalues to be lambda I plus. So here in this corollary, the statement states that lambda n plus 1 plus is greater than 0. That is, there exist at least n plus 1 positive eigenvalues. Then this lambda n plus 1 plus is equal to minimum over x1, x2, etc. xn, phi of x1, x2, etc. xn. Now what is phi? Phi of x1, x2, etc. xn is nothing but the supremum of norm x equal to 1 inner product Txx, where x element of span of x1, x2, etc. xn orthogonal or perpendicular. Okay, so just read the corollary once again. That is, if T is a self-adjoint compact operator, then lambda n plus 1 plus is equal to minimum of supremum of C. Phi is actually this, so you can consider this to be minimum of supremum of norm x equal to 1 in a product Txx, where x is an element of span of x1, x2, etc. xn orthogonal. Okay, so x is actually orthogonal to all these elements xi's. Okay, so then lambda n plus 1 is nothing but the minimum of supremum or minimum of maximum. So this corollary is also known as the minimax principle. That is because of the fact that lambda n plus 1 plus is nothing but minimum of supremum or minimum of maximum. So that's why it is called as the minimax principle. So keep that word in mind. So this is our corollary that gives us the value of the corresponding lambda n plus 1 positive eigenvalue. So let's just see how we can prove this corollary. The proof is pretty much simple. We just have to work on it. So first of all, let me consider the operator T restricted to span of x1, x2, etc. xn orthogonal. Okay, T is restricted to span of x1, x2, etc. xn orthogonal. Then using our previous corollary, using corollary 6.2.6, we get lambda n plus 1 plus is nothing but the maximum of inner product Txx, where x is perpendicular to EI orthogonal, where I varies from 1 to n. Okay, so this is what we get from the corollary. That is, the corollary states that the maximum value is attained if the positive eigenvalue exists, then the maximum value of inner product Txx will be the largest of that eigenvalue. So we are given an operator T and we are restricting it to the set span of x1, x2, etc. xn orthogonal. Then corresponding to this there exists some eigenvalues, and we choose by corollary the largest eigenvalue will be the maximum value, right? So it is maximum of inner product Txx, Txx, where x is perpendicular to EI orthogonal. Now just look at this definition. How have we defined phi in the corollary 6.2.7? We had defined x phi of x1, x2, etc. xn to be the supremum of norm of x equal to 1 inner product Txx where x belongs to span of x1, x2, etc., xn perpendicular. Okay, so this is how we have defined the function phi. Now just look at this. It is maximum of inner product dxx, where x is perpendicular to each ei. So if x is perpendicular to each, I'm sorry, you have to write this. So if x is perpendicular to each of ei, then I can say that x is perpendicular to span of ei, right? So I can say x element of span of e1, e2, etc., en, right? So from this I can say x is an element of span of e1, e2, etc., en perpendicular. Okay, so this is nothing but phi of, instead of x1, x2, etc., xn, I have e1, e2, etc., en. So I can say this whole term, okay, just look at this whole term is nothing but phi of e1, e2, etc., en. Okay, so I hope the concept is clear by the definition of phi. So this implies I get lambda n plus 1 plus is nothing but phi of e1, e2, etc., en. Now I have to show that lambda n plus 1 is the minimum of such phi's, minimum of the phi's, right? So lambda n plus 1 actually attains a value phi of e1, e2, etc., en. Now if we show that for any x1, x2, etc., xn, phi of x1, x2, etc., xn is greater than or equal to lambda n plus 1 plus, then what I can say, for any this phi is greater than or equal to n plus 1. So lambda n plus 1 plus is the least value of all such phi's. Okay, then lambda n plus 1 plus is equal to minimum of phi of x1, x2, etc., xn. Okay, so we can easily say this. So let us see how we can show this part, that is phi of x1, x2, etc., xn is greater than or equal to lambda n plus 1 plus. For that, let me consider an element y is equal to summation 1 to n plus 1 ai ei plus. Okay, I'm considering an element y such that inner product y xj is 0, that is y belongs to span of x1, x2, etc., xn perpendicular. Okay, y inner product y xj is 0, that is y is perpendicular to each and every xj's. Okay, so here I varies from 1 to n plus 1 and j varies from 1 to n. Now if this is true, what can I say? I'm just going to apply y over here, that is I is equal to 1 to n plus 1 ai ei plus comma xj is equal to 0. Okay, so this implies this is, I am going to take this summation common by linearity, ai inner product ei plus and xj's equal to 0. Here j varies from 1 to n. So I'm considering in this expression, you can see that ei pluses and xj's, these and all we have chosen arbitrarily already. We have already chosen these values, right? Corresponding to the eigenvalues lambda I, we get ei plus, and xj's are chosen from the Hilbert space. So these are chosen. So in this expression, the only thing unknown is these ai, right? ai's are the only ones which are unknowns. So if you consider this as a set of equations, here I varies from 1 to n plus 1, that is the set of unknowns is n plus 1, and the equation will be how much? J varies from 1 to n. So this forms a set of n, note that it is n homogeneous equation, okay, n homogeneous equation with n plus 1 unknowns. How many unknowns are there? N plus 1 unknowns are there, and n equation are there. So clearly, if there are n equations and n plus 1 unknowns, clearly there exists a non-zero solution for this system. Okay, there exists a non-zero solution for this system. So that is this AIs. We can determine these AIs can be determined. Okay, so this means y equal to summation AI EI plus x's, such that inner product yxj equal to 0. Okay. So I have found a y which satisfies this condition, that is y is equal to summation AI into EI plus, such that inner product yxj equal to 0. Now if we consider summation mod AI square to be equal to 1, okay, suppose summation mod AI square is equal to 1, then what can I say? I can say that if I take inner product yy, this will be nothing but inner product summation AI EI plus summation AI EI plus, right? So I'm taking summation AI common, so that is AI, and from the second portion if I take, it will become AI conjugate into inner product EI plus EI plus. EI plus EI plus is nothing but 1. So this is summation mod AI square, and if we have assumed that according to our assumption this is equal to 1, so inner product yy is equal to 1, this implies norm of y will also be equal to 1, right? So finally what I am going to say is, I can say that there exists a y which belongs to span of E1, E2, etc. En, such that inner product of y and xj equal to 0 and norm of y is equal to 1. Okay, with the help of this y, I am going to show that our required condition, that is phi of x1, x2, etc. xn is greater than or equal to lambda n plus 1 plus. So let us see how we are going to do that. So for that, since inner product y xj is equal to 0, that is y is an element of span of x1, x2, etc. x orthogonal, which we have stated before. So for that, what I am going to do is consider by definition of phi of x1, x2, etc. xn, it is actually the supremum value of inner product txx, right? Where this x is an element of span of x1, x2, etc. xn. Now we have obtained y to be an element of span of x1, x2, etc. Orthogonal, etc. xn orthogonal. So by definition of phi, I can say that this is definitely greater than or equal to inner product tyy, right? Because phi is nothing but supremum of all such ty's. The only condition was y should be an element of span, and we have assumed by our consideration or by our assumption y was an element of span. So by definition we get phi is greater than or equal to inner product tyy. Now let's just simplify this. This is nothing but inner product t of summation ai ei plus into summation ai ei plus 1. T is a linear operator, so this is nothing but summation ai into t of ei plus comma summation ai ei plus. Again I can take the summation ai, which are constant, from the second variable it will become conjugate into t of ei plus ei plus. So this is modulus square, that is nothing but 1. So this is I can say this is ai whole square. T of ei plus is nothing but lambda I plus ei plus into ei plus, right? So this is summation ai square into lambda I plus, inner product ei plus is nothing but, again it is 1, right? So let me just write it out again. I get phi of x1 x2 etc xn is greater than or equal to summation mod ai square into lambda I plus. Now this is each of these lambda I plus by our assumption will be greater than equal to lambda n plus 1 plus, okay, and this summation value is assumed to be 1. So I get this value is greater than equal to lambda n plus 1 plus. Why was this? This was because lambda 1 plus is greater than equal to lambda 2 plus is greater than or equal to etc greater than equal to lambda n plus 1 plus. So I can consider each term to be greater than equal to lambda n plus 1 plus into summation mod ai square, which is nothing but 1. So I get phi of x1 x2 etc xn is greater than or equal to lambda 1 plus. So that was our proof of the corollary. So we had assumed that two things. We had to consider our expression, our y, and that is an important point which has to be chosen, and with the help of that, the first portion, that is lambda n plus 1 is equal to maximum of phi of x1 x2 etc or maximum of inner product t of xxx is obtained from the previous corollary. And to continue or to move on with the proof, we have to consider an element y, and with the help of y we will show that the corresponding element, that is t of yy, inner product t of yy will be always less than phi of x1 x2, and with that expression we get our required condition that lambda n plus 1 is less than or equal to phi of x1 x2 etc xn, which gives us the required condition. So that's it for today's session. So thank you.